turned too far over time. It's unfortunate because this is the important part. But, okay. So today we will discuss Shor's algorithm. I already set this up a little bit in the last class. And although normally Shor's algorithm is conveyed as an algorithm for finding the prime factors of a number, the way we have introduced it, it's going to look just like Simon's algorithm, where Simon's algorithm was a period finding algorithm, right, for numbers in the binary strings and to find out their properties. And now we are introducing the Shor's algorithm, which again we are going to divide it up into two parts. One is the quantum portion of the algorithm. And that's the first part that I'll discuss, which is the quantum portion. And then we have a pretty, beyond just the quantum portion, which is fairly straightforward to understand, we'll also have to figure out a sort of number theory portion of this. Just because, as I was explaining, that we are now dealing with groups in the number integers, in the finite integers. And these groups, just like the groups F to N, which was the Shor's, the Simon's algorithm, solved the number, the period finding for the group F to N to R or Z, right? That is, it took functions that were, in these binary strings and mapped them onto other binary strings, and it then this function, we found the period for it using Simon's algorithm, right? That was Simon. Okay. And in this Shor's algorithm, the quantum part of this is that we assume, and I will say later a little bit about this assumption, that is, we are assuming that there is a quantum circuit. So this is that standard black box or oracle type approach to quantum computation, where we say we have a quantum circuit QF, okay, which implements F, which is of the group Zn going to something, of course, again, this could be like binary strings, 0, 1 up to M. Again, I go back to my favorite analogy of the guitar strings or guitar notes in 0, 1, M. Okay? So every binary string that is M bits long represents some symphony or note, okay, or function in this case. Okay, the output of a function. And the Zn, as I explained, are the integers basically 1 up to n minus 1. Okay, that was what we introduced in the last class. Okay, and this function f, we are promised this function f of x is L periodic. That is, for all x, f of x equal to f of x plus L, which is also therefore equal to f of x plus 2L, etc., is true only, that is, i.e., f of x equals f of y only if and only if y minus x is a multiple of it. Okay? So this is the quantum portion, which is, we are given access to such a circuit, okay, QF. And at the very end, I'll come back and say something about how can we construct this QF, okay, which will carry out this task. But we are given this circuit which carries out, which implements this function f, which has this particular property that it's periodic, okay, so that f of x equals f of y is only true if y minus x is a multiple of this L, and our goal in Shor's algorithm is to find this period L. Okay? And of course, we should be thinking about the n as a very large number. Okay? So, suppose, in fact, n is some large number, 2 to the m, okay, of that nature, assume, okay? And assume L divides n. Okay? So that the set of integers from 1 up to n minus 1 can be broken up into these multiples, L, 2L, etc. The problem, of course, is that if n equals this this kind of even number, which is a power of 2, if it's exactly equal to that, then we know clearly the only things we have to check are the integers 1, 2, 4, 8 up to 2 to the n minus 1. And one of these will be a divisor of n, and there's only n possibilities here, right? 1, 2, 4, 8 up to 2 to the n minus 1. We can easily see there are only n possibilities. It will be easy to check. Okay. So you might say, well, this is too easy. Of course, if n is on the order of 1000, let's say it's a 1000-bit number, right? That's still 1000 divisors you have to check, but that's easy comparatively with modern computers. Okay. So for today, the problem is, as you'll see when we get to the quantum Fourier transform of this, typically we want numbers n which are powers of 2 to the n. Remember, we had those bits that were, we had a bit string and then we used the quantum Fourier transform on it. So if we want to implement quantum Fourier transform, typically we're going to need some numbers that are in fact powers of n. At the same time, if it is actually exactly a power of n, then the entire quantum algorithm seems silly because we can just check all the divisors of this n by just simply looking at this series 1, 2, 4, 8 of it. So I'll show you later that even if n is not an exact power of 2 to the n, everything that I say will go through. Okay, so we can, it's actually a fairly straightforward thing. You round off the number n to the nearest power of n for the quantum circuit part. The quantum circuit returns some integer which will be dividing the integer nearest to this power, to this n, which is a power of 2, and from that we'll be able to find the exact divisors. Okay, so that's the approach for the problem. But for today, so remark 1, for today, assume n not equal to 2 to the n except when implementing DFT. The quantum Fourier transform. This may seem a little bit contradictory as I just explained, but when we come back at the end, we'll see that it's okay to assume that n is not equal to 2 to the n for everything else, and then assume it's equal to 2 to the n just for the quantum circuit part, and the resulting output will be close to being a divisor for n. Okay, this is the and even then we don't need to technical. Okay, when we find the last part of this algorithm, we'll see that this is indeed true. And the second remark. Right, which is a corollary for this. Remark 2 is we will see Shor's algorithm works even if L does not factor n. That is, this is typically represented by L factoring n is typically represented by this this notation L slash n, okay, L vertical slash n, and then if you want to say it doesn't factor n, you put a thing like this. So even if L does not factor n and L periodicity fails, exactly at the mod n wraparound. Remember, this set of integers Zn represents the remainders when you take any large number and divide it by n, right? When you take any large number, some other number b, big number b, and divide it by capital N, you get a remainder. And these remainders by definition will be any number from 1 up to n minus 1, right? So if L is one of the numbers, if L doesn't quite divide n, right, in this set of integers, then you can split up this set of integers into those that are, that is where f of x equals f of x plus L at various points, and then right as you approach the end of this group, Zn, you may fail because f of x plus L, where x is close to the n minus 1, will go around back to the beginning of the group. Okay, so that's the only issue, but we will see that that Shor's algorithm will work even if this L periodicity fails exactly at the very end of the group. Okay, so let's do the algorithm. Okay, and then at the end we'll come back to why this is all working even when things aren't perfect. Okay, so just like Simon's algorithm, we follow the usual approach, which is first rotate the input registers. So here is our input registers. Again, I'm going to use the notation to simplify writing all the all the lines for each n-bit integer. I'm just going to say ket 0 to the power n, which is just the direct product of all the individual qubits initialized into the state 0. This is the input register, right? And then as usual we have the output or ancilla register, whatever you want to call it. That is the m bits that we are going to write the output into. Okay? And as usual, we will carry out the Hadamard to the power n, which will now create a uniform superposition of all the possible input strings. Okay? And then we will apply our magic quantum circuit, QF. Okay? As I said before, the magic quantum circuit gives us the answer. I have not told you how to construct it. But you can trust me that constructing this circuit will not be difficult if we have an equivalent classical circuit that carries out the function f of x. Okay. The answer here, right, is 1 over root n summation x equal to 0 up to n minus 1 summation x ket x times f of x, where now this f of x is in the in the output registers. That's what this function f does, right? The QF does. And now measure, and this f of x, as I said, I'll just call it A. Maybe it's a note in a musical symphony, whatever you want to call it. A hash, B hash, represent D sharp, A sharp, B sharp. If you're familiar with any kind of musical terminology, you'll know that this is kind of the idea of this function, but you can also think of it as just a number, a number in the space of m-bit strings. Okay? And we measure the output. We put measurement on the output registers, which are the m bits, okay, of the output register. Okay. When we do, we'll collapse this function to some value f of x star, okay, which I'll denote by the note s. Okay. So when we measure the output register collapses to state S star, which is equal to some f of x star. Okay? That's the output. Now let's look at how many times each of these letters that are in the string are going to appear in the output. Okay? Since this is a uniform superposition and f of x, right, is periodic with the period L, L plus 2L, etc. Remember, when we go back, f of x is equal to f of x plus L is equal to f of x plus 2L, etc. Right? And we are getting this output S star, which is f of x star. We know that therefore each value S star is used n over L times. Because there are n values in the input register, okay? There are n possibilities, there are n total number of possibilities for the input register, okay? And S star is those values which are separated by the period L. Therefore, each value S star is used n over L times in this output after measurement. Okay? And the probability that this letter appears in the output, or the string appears in the output, each letter string appears with the probability, because we created a uniform superposition to start with, each of these x values appear with the probability 1 over n, and I've just said that it will be repeated n over n times, so which means 1 over n times n over L equals 1 over L times. Okay? 1 over L probability. Okay? Therefore, so if I get readout S star, which belongs to the output, the state collapses. And the collapse is the superposition square root L over n summation of all those x such that f of x equals S star, right? Just like in Simon's algorithm, all those values that are possible for f of x equal to x star, those values of x, those will be in the input register, and in the output register will be the value of the S star that we want. Is this part clear? Not clear, just stop me. Okay? It didn't make sense. F of x is the function whose period we are trying to find, and it breaks up, you can think of it as breaking up the set of integers from 1 up to n minus 1 into into groups of L, meaning at every value of L, f of x has the same value. At every value of the integers which are separated by L, f of x has the same value. And there are a total of 0 up to n minus 1 integers that you could think of. Okay? And therefore, it breaks up this set into these sort of like, you can, as I'll even sketch in a minute, into this uniform spikes which are occurring, which are spaced by a period of L. Okay? And what I've just shown you is that whenever f of x equals S star, this superposition will collapse into, or this output superposition after the measurement will collapse into this one, where the values of x that are separated by L, now each of these x values will be separated by a value x, x plus L, x plus 2L, x plus 3L will be in this in this input register. So essentially this is just like Simon's algorithm. In Simon's algorithm, after the collapse, it went into x and x plus 8. Okay? Here, because it is L periodic, and the value of L might be anything, it breaks up into x plus L plus x plus 2L, etc., where each of these x values basically, or each of these values is such that f of x is equal to the value s star that appeared on the output register. Okay? And we're going to discard it. We don't care about the value at all. Because the important information is the period of this function L. Remember, that was our goal. At the very beginning I stated, the goal is to find the period. We don't care about the actual behavior of the function f or the values that it outputs. We really only care about the period capital. And that is encoded in this giant superposition. Okay? Which has all of these values x, x plus L, x plus 2L, etc. So our goal now is extracting this period L from this superposition. And of course, the reason I set it up this way is that obviously what I'll do to the input registers is apply the quantum Fourier transform at this point. Okay? So I apply the quantum Fourier transform n at this point. Okay? But before I do that, let's look at the properties of this superposition, because then immediately the behavior of the quantum Fourier transform will help us to understand how we can extract the period L. So we can think of this summation of all these values of x as representing a function of x, just like before. Remember, I've said that any such superposition can be thought of as some function. Okay? And this function in this case is a function that I'm denoting, so this I'm going to represent as defined as gs star. Okay, this is some giant superposition, gs star, and gs star is equal to summation over x of gs of x times x. Okay, and clearly 1 over square root of n, because it's over all the values of n. Clearly comparing these two kets over here, this summation and the way I wrote it here, this function gs of x, right, is simply the function. It is square root of L if f of x equals s star and 0 otherwise. Right? Because by definition, that's what this summation says. Okay? So our function here is then, if I were to sketch it on the line x, and this is gs of x, okay, and starting with 0, ending at n minus 1, whenever x is such that f of x equals s star, the value that we read out on the output register and discarded, so in fact I will write here s star, right, that's the output value, and we have discarded it. Okay, we don't care what it is. In fact, as you will see, we can set it equal to 0, doesn't matter. Okay? It doesn't matter what the value of s star is. I'll prove that statement in a minute, but it's pretty simple. And every time f of x equals s star, I get a peak in this function s of x. And of course, that's going to happen every time this value x, for example, if this was x star, this is x star plus L, x star plus 2L, etc. Each of these will be represented with an output value gs star, sorry, not s star here, but with the value square root of L, according to this function over here, because that's exactly what this state ket defines. So the value of this function gs of x is square root of L at every value of this x star plus L, x star plus 2L, and so each of these is separated by L. Sorry, I obviously didn't sketch it very well. These are all evenly separated values, etc., which are all equidistant by L. Okay? Up to the n minus 1 wrap around, and as I told you in the just before we started, even if L doesn't quite divide the n, this will all end up working out. Okay, as we'll show later. And these values, f of x star is equal to the s star that we have read out on the output register. Okay, so that is nice. And now when I apply the quantum Fourier transform, what is going to happen to this state? That is our next question. Okay, so this is the circuit, and this is it. This implements Shor's algorithm right here. Okay, that's all you need to know about Shor's algorithm. It looks just like Simon's algorithm, except that instead of applying the Hadamard Boolean transform on the input register, I applied the quantum Fourier transform that I introduced in the last class to the input register. Okay, and remember in the last class I showed you that this QFT n can be done with on the order of n squared gates. Okay, so if you add up the number of gates, which I've had to do, which I'll do at the end, there are n gates obviously in the Hadamard transform. Okay, each one is just a single application of Hadamard. There is QF, which calculates the function f of x. I haven't said yet how many gates I'm going to require for that, but you'll see it's actually on the order of n cubed, not very much. Okay, and then QFT n, which requires n squared number of gates approximately. And therefore, we will see that this is all polynomial in the number of bits n, whereas any classical algorithm to do the same behavior will require an exponential number of gates, 2 to the order n over 2 approximately. Okay, so after we have employed the DFT, what is going to happen? So I'm going to remove or erase the sketch of the quantum circuit. Just remember it, because this is the famous Shor's algorithm. Okay, and that's all there is to it. Okay, it looks very simple. But of course now the magic comes about, which is how does this periodicity in the function lead to factoring and so on. But before I, so let me just finish up this claim that I made over here. So what happens when I apply the QFT? Okay, and as I said, it's on the order of n squared gates, which I showed you in the last lecture. The state now, after I apply, so now when I apply the QFT to this state ket, to this GS star, I'm going to get a new state at the output, okay, of the QFT, which is again some superposition, obviously, of say y equal to 0 up to n minus 1 of GS star of y at y, okay, because remember this S star, I'm still keeping that notation for the for that, and this is of course, as I showed you in the last class, is the Fourier transform, which is GS star of y, okay, is the strength of the discrete cosine U S in GS star, okay, or UY, sorry. Okay. Therefore, when I measure now the readout, S belonging to 0, 1 up to n minus 1 with probability GS star of y whole square. Okay. So when I measure the readout now on the input register, I will now get the strength of this cosine on with the probability GS star of y. Basically what I'm saying is you get a Fourier transform of this function GS star of x as the coefficients in this new superposition. And this GS star of y, as I said, is the Fourier transform of this function GS star, GS of x. Okay, does that make sense? The coefficients in the new superposition that occur by applying the unitary operator QFT on this state over here, on the state GS star, okay? This new state has as its coefficients the strength of the discrete cosine function uy in GS star with the probability GS star of y whole squared. And now I claim that this GS star of y probability does not depend on the actual value S star. Okay. And of course the question is, why are we doing all this? And I am going to say that we will hope this gives us, remember we wanted to get this period F, okay? And the question, and I claim that in fact by taking this Fourier transform, I'll get some insight into this period F. And of course from our knowledge of Fourier transforms and physics tells us that if a function has some period L, then the corresponding Fourier transform will have some period 1 over L. Okay, some multiple of 1 over L, like in the Brillouin zones and solid state physics. All this tells us that we are expecting that this function GS star of y will have some periodicity 1 over L, and therefore we'll be able to extract some information about L. But exactly how to do that is the trick, is why we need some number theory results that I'll introduce after I finish this quantum notion. Okay, but first the claim is GS star of y whole squared does not depend on the value S star. So it's independent completely on S star. Because remember, this function f of x equal to S star is where we start this superposition. That is the value of x star, the first one that satisfies f of x star equal to S star is where this function starts, and then it of course occurs with the periodicity L. And I'm saying it doesn't depend on the start point, basically. Doesn't depend on the value of S star. This periodicity or this Fourier transform doesn't depend on the starting point of this function or the offset of this function from 0. Okay? And of course, again, from our knowledge of solid state physics, Fourier transforms, etc., we know that a shift in the function, if I were to shift this function to some different value, will just result in a phase in the Fourier transform. So we're going to use that result now. We're going to prove it again for this discrete Fourier transform, but hopefully again you have some insight from your knowledge of solid state physics and so on. So again, if it does not depend on this offset S star, we can simply set the S star equal to 0. And we can simply say, we are just going to assume that the output registers gave us the value 0. Remember I told you, if the output was equal to S star, we were going to throw it away. And in this case I'm saying, I can even set it equal to 0, whatever the result, it didn't matter. And I can get the same periodicity on the output. Okay? So that is the sort of corollary of this proof. And the proof is just coming from the property of Fourier transforms, the shift property of Fourier transforms. Which is, if f is a function which maps integers onto the complex numbers, and y is some such integer Vn, and define the function f plus y, the superscript Zn, again going to complex numbers, by f plus y of x equals f of x plus y, then f tilde plus y of s, sorry, I keep switching between s and y sometimes over here. I already use s star for the value of the output register. Here s is now denoting, let me call it, say, omega. Maybe that would be good. Did I use omega? Oh yeah, I used omega also for the complex root of unity. So in this theorem proof, then the complex plane, the complex plane, or sorry, not the complex plane, but the Fourier transform plane, which is y over here. If I use y again, let me change the shift register. Maybe I call the shift register as some other. Let's call it a, maybe. Yeah, that makes more sense. Let's call the shift by value a. Okay. Plus a, and now I can go back to using y for the Fourier transform variable, okay, is equal to f of y times some nth root of unity, a phase factor, right, like we defined last time. It's just e to the minus 2 pi I over n to the power some integer, some nth root of unity, and this therefore has magnitude 1. And therefore does not affect the probability with which I will get the measurement readout. Okay? Again, okay, the proof of this is pretty straightforward. I'll just quickly sketch it. Remember this function that we got on the input registers now. Okay, gs of x, which is the original state that we are trying to decompose into its sines and cosines with the discrete Fourier transform, has the appearance of this L periodic train of pulses or spikes in the x domain. Okay. Okay, proof. Okay, very simple. Since we already know a lot about Fourier transforms, this should not surprise you. F of plus a of y, which is the Fourier transform, which is shifted, is simply taking 1 over n. Remember from our earlier last week, this is just taking these values and multiplying by the coefficients us, x, uy, x, star, okay, f plus a of y. Okay, so it's the summation which gives us this value. Okay, all right. So this is like omega or something, and this is the t of our standard Fourier transforms. And I introduced that in the last class as well. So it's just hard to keep track sometimes of all the different notations, and I should try to do better on that. So let's be careful. Uy star of x times f of x plus a. Okay, and of course we can switch variables in the summation. This to some new variable z equals 0 n minus 1 u y of z minus a star f of z. Okay, so I just switched z equal to x plus a. Okay, and then this will automatically happen, right? And of course, I had to justify that the summation still goes from 0 up to n minus 1. Well, and the reason for this is since z equals x plus a implies x equals z minus a, and as x runs from 0 up to n minus 1, so does z, right? So there will be always some value, let's say when when x equal to a, that you will get back the same summation. Right? And by the character property of those functions us of x, which is simply because they are nth power of unity or nth root of unity that I introduced earlier, let's make sure uy star of z minus a is going to be uy star of z times uy star of minus a. Okay? That is the character property or the multiplication property of these functions uy, or simply because we already showed that uy of z is simply the power of e to the 2 pi, we can just we also know that this will be true. Okay, and so therefore that function or that f plus a of y will be equal to 1 over n summation z equal to 0 n minus 1 uy star of z uy star minus a times f of z. Right? And this is equal to simply uy star of minus a times the original function f of s, f of y, Fourier transform. Okay? Because this guy is just some constant, right? uy star minus a is not part of the summation, so it's just a constant phase that's multiplying each term in the sum, and everything else in the sum is equivalent to the Fourier transform of the function z, so I can pull it out and I get this. Okay? And this guy has magnitude equal to 1, because if you want explicitly uy star minus a is simply omega, the nth root, omega n, remember, was e to the minus e to the 2 pi I over n. So this is omega n to the power minus y times a, and this is conjugate, and so this is just omega n y. Okay? And therefore we have proven the result, which is that the in the spike train, no matter what the offset value of that spike train was, the output of the Fourier transform is the same as the initial one, with the output set to 0, multiplied by some phase factor which is given by this answer. And since an overall phase of the Fourier transform does not affect our result, we just discard the phase factor and simply keep only the part with the initial output or registers set equal to having a 0 value. Okay? Okay. So we may assume, therefore, that in that output registers, so we may assume so this is just some overall phase, global phase in the Fourier transform, so I can discard. Okay. So we may assume, in fact, also we can assume that S star, the output of the Fourier of the function f, is simply the same as what would be set by setting the input registers to 0. Okay. So then that function g s star, remember that I had sketched for you, g s star of x is the simplest L periodic spike train, which is it goes from x equal to 0 up to x equal to n minus 1 with a period m. All of these are separated by L, and the function starts at the value x equal to 0, whose now Fourier transform we have already written down. So now I will claim the next theorem that we need to know, which is again just a property of the Fourier transform having to be preserving the normalization of the state. Okay. This is like Parseval's relation for, do you guys know Parseval's relation for Fourier transforms? That is that the integral of f of t modulo squared is equal to the integral of g of omega, f of omega modulo squared d omega. Same thing, except now I'm going to prove it for this peculiar discrete Fourier transform case. So theorem. If now g of x is this simplest, and we know the value of this simplest is root L, it has to be to preserve the normalization. So if g of x is equal to root L for x belonging to the set 0, L, 2L, etc., which is the subgroup of Zn generated by L. Okay, just a remark, you may not care, it's just arithmetic if you like. It's just a set of integers and is 0 otherwise. Then the DFT G tilde of y, again, which maps integers to the complex plane Zn, is simplest n over L spike plane. And what I mean by that is G tilde of y is equal to, now I claim, is 1 over root L if y belongs to 0, n over L, 2n over L, etc., 3n over L, and 0 otherwise. So the claim, which I'm writing over here in sort of graphical format, that G tilde of y, this is y in the same sort of reciprocal space of this transform, will have the value 1 over root L at every value y equal to 0, n over L, 2n over L, etc. up to what? And that's what we are going to prove. Okay? Well, the proof is actually very simple. So we know it has to be 1 over root L because when we take any function, any ket g, okay, remember g, which I erased now, g was the ket which was composed of 1 over root n gs star of x. I don't even care about s star anymore times x because s star has been set equal to 0. If g is this ket, then carrying out the DFT to the n gave us the new summation y equal to 0, n minus 1, g tilde of y ketwise. Okay. Which implies, we know this by this relation, this implies that summation y equal to 0, n minus 1 modulo g tilde of y the whole square must be equal to 1. Okay? And we see immediately from this other statement that therefore, since the values where g tilde of y is non-zero is only at 0, n over L, 2n over L, etc. Therefore, if we just show the first part that it is in fact 1 over root L, here this g tilde of s or g tilde of y has non-zero values. Implies that these g tilde of y must be equal to 1 over square root of. Right? So the proof, and what's the consequence? Before I go on to describe the proof, the consequence of this is very nice. Okay? So if this theorem is true, right? I didn't prove the full theorem yet, but if this is true, then the output of the DFT, right? The output of the DFT is this guy over here, which is of the form 1 over root L, okay? Summation over all values of y such that y dot L equals 0, modulo L. Okay? Remember, if the only values of y belong to this set 0, n over L, 2n over L, etc., then y times L must be 0 modulo n, right? It must be a multiple of n, clearly. Okay? And if y dot L is a multiple of n, that means we have factorized n. Okay? So this is true. Then, and therefore, when we measure this, now if we measure the input register after the DFT, it will collapse into one of these states. Okay? With the equal probability given by 1 over square root of it. Okay? Or 1 over n, sorry, because the modulo square, right? Which means that I will get some output answer which belongs to the set n over L, 2n over L, 3n over L, etc. Okay? And I know what that output value is, y, which will be read out on the input register, what I call the input register. So I'll have one of the factors of n over L, so I'll just multiply out and I'll get the answer for what, okay, that of course using one of these numbers. So let's say implies if I measuring reads out some random y star belonging to 0, m, 2m, etc. up to n minus m, where m equals some n times n divided by n. Where m is of the form n divided by n. Okay? So I'll get something of this form. It has to be of this form n divided by L. All the multiples of m which is equal to n over L, but which are less than the capital N. Okay? That will be the output. So if I get two of these, let's say I repeat the algorithm once or twice, then from a few of these, I'll discover the value L equal to n divided by n, because I know the input n, right? Okay, I know the input is some capital value n. Okay, and I needed to find the period of this function L. Okay, And I've discovered that each time I read out, I'll get some m, which is n divided by l. If I have two of these, I can find the greatest common divisor, and that will give me the value of the period L, which was the original goal of the experiment, of the program. Okay. And of course, the question is how common is this, or how often does this happen, and so on. But before I do that, let me read out so from a few multiples. Can discover m. Right? Each time I collapse, I'm going to get m or some power of or some multiple of m. So it's easy to find the value m after a few of these trials. And once I discover the value m, I obtain L equals simply n over m. Okay? So the trick is, if I can efficiently discover this capital M each time, then I know what L is simply by taking n and dividing by this m. So, but first, as I said, I'll prove the theorem above, which I just stated over. Proof of the theorem, okay? Again, we go back to sum over y, g tilde of y whole squared must be equal to 1. That was just a statement of the normalization of this theorem. And g tilde of y, by definition, is the Fourier transform of the function g s of x, or g of x. In this case, I've dropped the value s anymore because the value of s does not matter. I'm going to omit all these summation indices and so on. Just as I say, sum over x, and that is just g of x. Okay, so drop that s value because it doesn't matter. And this, now I substitute the value for g of x, which is the square root of L, which is which was 1 over n. Let's see, I'm missing a square root of n. Where is that one? This may be square root. So this should be square root L over n. Summation now over all values x equal to 0, L, 2L, etc. of uy star of x, which is equal to square root L over square root L over n. Okay. Summation x equal to 0, L to L of, now I put in the character which is the nth root of unity minus, therefore, y x. Okay. Uy of x is simply the nth root of unity to the power minus y x. Okay. And now each of these values y is of the form 0, L, 2, L, etc. So this is simply, I can write it as 0 square root L over n times some integer m, okay, times summation j equal to 0 up to m minus 1 omega n to the power minus jl times x. Okay. And why? Because if this indicator or this summation runs over all the values 0, m, 2m up to n minus m, then this jl times the value of x must run over all the similar multiples up to the value of n minus m. So that is, if the reason, which I always, sometimes when I'm telling you about reasons, I'll put this sort of thing, which is that if y belongs to the set 0, m, 2m, etc., as we said it does over here, then j, l times, was that x? If x belongs to the set, then jl times x is going to belong to jl times some k times m, where k is some integer, and this is the same as writing jk times Lm, which is the same as jk times the integer n. Okay? So therefore, this summation can be written as square root L over n times m is equal to some times summation j equal to 0 to m minus 1 omega n minus jk times m. Okay, and therefore this m of course is n over L. So maybe I was correct in the beginning. This should not be n. This should be 1 over square, not square root of n, but 1 over n. And I have to verify this because it's obviously important point. How did I miss this? Let's see. Go back. Okay, just notice this. I had to justify that this was not 1 over square root of n, but 1 over n. These normalizations always are a little bit tricky. So this is square root L divided by n, and m of course is n over L, and therefore this is 1 over square root of L times summation j equal to 0 up to m minus 1 of 1, and this is equal to 1 over square root of n. Okay. Because omega n to the minus jk n is equal to simply 1, because omega n is the nth root of unity raised to the 1 power is simply 1. Therefore, 1 to the minus jk power, which is an integer power of 1, is simply 1. Okay. So we have shown that each of these g tilde of y is indeed equal to 1 over square root of L when this values of y are exactly these multiples from 0, m, 2m, etc. And we have shown that since it's only equal to this 1 over square root of L, and there are L such values, the sum of these modulo squared is going to be 1, which means it must be 0 at every other point in the y plane. And I have to verify this square root of L business, square root of n or 1 over n business here a little bit. So I need to verify that for you. I thought it was 1 over square root of n, but instead I'm getting 1 over n. It has to be n because that's what it is in my notes, but now I'm a little bit doubtful. So I'll go back and check on that. Okay, so what has all this given us? Well, it must be because the answer works out, but at the same time I'm a little bit doubtful whether I fudge the definition there somewhere. So I'll have to go back and check that for you. Okay, how much time do I have? Almost out. Okay. Okay, I want to summarize what we've done. Because the rest of this is now, we are done with the quantum portion of Shor's algorithm, and the rest of this is all going to be about number theory of how this can be used to prove that we can efficiently get factors of this thing. So the summary is, given QF, which is for an L periodic function, which takes Zn to some strings 0, 1 to the power m, we can, first of all, we load the function f into the superposition, load f into the state ket, into ket. That requires n Hadamard's and 1 QF unitary operator, which I have not told you how to construct, but we will assume that there is some classical circuit that can construct this function, and therefore that there should be a corresponding quantum circuit. And in fact, it turns out that this will require on the order of n cube gates. Then we apply the DFT, which is on the order of n squared gates. And then we measure. The measurement gives random, uniformly, okay, some value y, which belongs to the set 0, m, 2m, etc., where m equals n over m. Okay? So the point is, if I repeat this a couple of times, okay? So repeat the claim that I make now is this. We just need 2 repetitions basically. Repeat twice Shor's algorithm. Each time we'll get some result, k1m and k2m, for random 0 lesser than or equal to k1 or k2 which is lesser than m. Right? We'll get some random multiple, one of these, in this set. Okay? 0, 2m, 2m, etc. We'll get one of these results each time. We repeat it twice. We get 2 such random results, which are some random integers k1 and k2, which have to be less than, of course, m. Okay? So what is the how do we find m? Simple. We use the GCD, greatest common divisor of k1m and k2m, which by the property of greatest common divisor is k1 comma k2 times m, right? And there's a very good chance that this is 1 times m with high probability. That is, the possibility that each of these multiples, say 2, 3, etc., has a common divisor that is other than 1, greatest common divisor other than 1, is quite low. Okay? How low? We can quantify it. But again, at this point, I should say again, at this point we have stopped doing the quantum stuff as far as Shor's algorithm is concerned. Okay? And all we are concerned about is showing these kind of number theory results. In fact, almost everything from now on that I talk to you about will be number theory stuff. Okay? And some of it is, which is why I brought the book. That is, some of this, I've proven some of the results slightly differently, but a lot of it is in Mermin, quantum computer science. I recommended it as part of your homework assignment to read some of these pages, which might clarify some of the number theory stuff that is behind all of these results. Including things like, why finding the period of this function is the same as factoring, okay, is equivalent to factoring. Okay, so by the way, GCD itself is a classical operation, and again can be done in less than n squared steps for n bit numbers. Okay, so that also is not going to add too much time to our algorithm or too many steps to the algorithm. And so what I have to prove to you is the claim that for k1, k2 randomly chosen from the set 0, 1 up to L minus 1, right? Which is as represented by this, the probability that the GCD of k1, k2 is equal to 1 is greater than or equal to 50%. Okay? So that is a thing that I have to prove. Okay? Proof, pretty straightforward. So might need only like 2 repetitions before the probability already becomes greater than 1. Okay? Equal to 1, sorry. So probability that k1, k2 both not equal to 0 is pretty high. Even if, for example, even if L equal to 2, right? Even if L equal to 2, the possibilities are 0 and 1, and the only way in which both k1 and k2 are going to be 0 is if they are both 0, which means it's already greater than or equal to 1/4, right? Because the probability is only 1/4 that they're both 0. So already it's starting to drop with just like for the case even when L equal to 2, and you can put further bounds on it. It's like 1/2 to the m or something like that. Okay, but even for L equal to 2, it's greater than or equal to 1/4. Okay, so we'll assume K1, K2 is not both 0 at the same time. Okay, and now, as I said, let us prove this probability. To do this, I'll assume that I can choose some prime P that factors K1. Okay? Just choose some prime P. Okay? And if P factors K1 and P factors K2, that's bad. Throw it away. Okay? Alright? Just throw away this P. Okay? So, the probability that this happens, that is the probability that P factors both K1 and K2, is equal to the probability that P factors just K1 the whole square. Okay? This is because if I divide up the set 1, 2 up to L into primes, okay, we are set up to L are in, and we are trying to find out how many of these are in the set P, 2P, 3P, etc. Okay? So that the less than 1/P fraction of numbers in this set are in this set. Okay? Because it's like saying, just consider something, simple examples, right? If I want to take a number which is say divisible by 2, right? Then you know already half the numbers can be thrown out. Okay? Right? Because every number that's odd is no longer allowed in the thing, in this list. Similarly, if it was 3, then the number of numbers which are say you can divide up the number line as 1, 2, 3, throw out that number, 4, 5, throw out 6, etc., etc. So 1/3 of the numbers are gone, right? Again, and so in this way, if P is some number, then we can throw out 1/P fraction of all of these numbers already from this set, because they will be in the set P, 2P, 3P, etc. Does that make sense? Okay. And that's why this, therefore, must be lesser than or equal to 1/P squared. Okay, I'm out of time. Just finish this. Finish the calculation here quickly. So if there is no such bad P, then GCD is 1. Therefore, probability of any such bad prime number which factors both K1 and K2, and therefore the GCD is no longer 1, is therefore lesser than or equal to the probability, let's say 2 factors K1, K2, plus the probability 3 factors K1, K2, and so on and so forth, right? This will be a set, and this will be lesser than or equal to, according to this inequality that I just wrote down, lesser than or equal to 1/2 squared plus 1/3 squared plus 1/5 squared, etc., which of course is not possible to evaluate analytically, but we can already, by just evaluating the first few terms in the series, we can show that this is on the order of 0.45. Okay, and You can keep evaluating that using Mathematica or something, and therefore the probability of a good choice of K1 and K2, right, is equal to 1 minus this, probability bad, and therefore this is greater than or equal to 0.55, that is greater than or equal to 50% as promised. Okay, so we have completed sort of the demonstration that we can find the period L with pretty good probability using the Shor's algorithm, and once we know the period, my claim is knowing the period is equivalent to factoring. Okay, and this is the part that, as I mentioned, is in the number theory results that are in Shor's algorithm, that are in this textbook. I don't have time to go through that entire proof in the class. What I'll give you is I'll give you my notes, okay, on the proofs of these other further number theory results. They are not too hard to read, I think, and try to make sure that it is clear what we are trying to do. And also remember, I also mentioned at the very beginning that the assumption that this L exactly divides n, which n is a integer on the order of 2 to the power n, is not even necessary. Even if we get a value of L which almost divides 2 to the n, this capital N, that will be good enough for Shor's algorithm to find the exact factor that divides that integer n. Okay, that other part is also fairly simple to see by just looking at probability, the Fourier transform properties, and I'll put that also in this notes. But essentially, as I said, the rest of it is all just number theory results, and I'll give that in my notes. Because in the next class, what I want to do, I want to skip, because as I said, the parts of this that are from here on out were known even in the 70s and 80s about how, if you can find the period of these functions, you can find the prime factors of any number, was already known in the 70s from just number theory results. Okay, so I don't necessarily want to go over that. Plus, as physicists, most of us being here are not probably too interested in knowing exactly all those details. It is good to see them once, as always, right? Like anything else in some aspects of physics, you should know some of it. You should have seen it one time, But it's not necessary that you're going to use it all the time. Like, that's a computer science business of like knowing how to factor given the period of these functions. And as I said, what I like about Mermin's this chapter here is he even tells you that even finding the period is enough to break the RSA encryption. Okay, so and he explains how you do that in those pages that I assigned you for reading. He explains how knowing the period of these functions is enough to break the current encryption technologies. So already just by knowing the period of these functions, we can skip even the factoring part and go directly to breaking the period of, to breaking all the current modern encryption technologies. So already you've achieved your goal without the intermediate goal of factoring. Okay, the factoring is also a side result, if you like, out of that. Okay, they are equivalent to each other. So, and all that is explained very nicely in Mermin, so I encourage you, as I said in the assignment, to read that part. In the next class, what I want to tell you about is a little bit about entanglement, and because that is a very interesting topic, I want to discuss some types of like quantum games and paradoxes that come about from entanglement. Okay, so that will be our last class of the semester. Sorry I took so much extra time, but you guys need to come in a little earlier because I keep waiting for you all till like 11, 10 or something, and then it takes me more time to finish. So please try to come on time for the next class, and then next week we'll have your presentations. And I think all of you have selected topics now, so if any of you haven't, please tell me now. Okay? I think all of you did email me with the topics, and I'll put